If we think back to the formation of stars, you may remember that stars tend to form in groups. We generally call these groups of stars star clusters, and we're going to focus on these for a minute. Primarily, we'll focus on determining the ages of these star clusters. A star cluster is a grouping of stars that formed together at the same time from the same giant molecular cloud after an isolated trigger event caused star formation to begin in that GMC. Now, how do we know how long ago this happened? Well, the age of a star cluster can actually be determined if we were to plot all the stars of that specific cluster on an HR diagram. Some globular clusters, like Omega Centauri, the most massive known globular cluster in the Milky Way at a whopping 4 million solar masses, can be heavily concentrated, with several millions of stars to account for and plot, while others, like Jargovsky 1, are more sparse. We'll focus on their differences and what makes each kind so unique in the next unit, but for now, let's see what happens to the trends on the HR diagram when we plot all the stars in globular cluster M55. The 55th item in Charles Messier's catalog of undesirable objects in his hunt for comets, globular cluster M55 is home to almost 269,000 solar masses worth of stars, 55 of which have so far been found to be variable stars. But if we plot all the stars in M55 on an HR diagram, this is what we'll see. This HR diagram looks slightly different from the HR diagrams we've seen before. Now, this should remind us that the HR diagram is a tool, allowing us to see trends and patterns in different groups of stars under observation. The main feature associated with the HR diagram of stars in a star cluster is what we call the turn-off point of the main sequence, the location of which helps determine the age of that star cluster. Here's how it works. As previously mentioned, plotting all the stars of a star cluster on an HR diagram reveals the cluster age. All the stars in the cluster formed at the same time, but they don't evolve at the same rate. The most massive, hottest stars fuse their hydrogen very quickly because of their extreme mass. They're the first off the main sequence because they burn fast, burn bright, and die young, much earlier than the lower mass main sequence stars that begin to follow suit. When we reach the current era and no other stars have evolved out of the main sequence phase, the position of the turn-off point can be used to calculate the cluster's age. The way this works is because each spectral class has a different main sequence lifetime. This means that the amount of time a star stays in the main sequence stage of its life is different according to its spectral type. We can use this information to determine how recently the stars in the cluster evolved off the main sequence, thus revealing the age of the star cluster. So what are the main sequence lifetimes in years of each spectral type? An O-type star stays on the main sequence for only 3 million years, and that's a short period of time in the grand scheme of things, as you'll see. B-type stars stay on the main sequence for 15 million years, A-type stars for 500 million years, F-type 3 billion years, and notice now that we're in the realm of billions of years, not millions anymore. And then G-type, K-type, and M-type stars each have a main sequence lifetime of 10 billion, 15 billion, and 200 billion years, respectively. It's worth noting that the K and M-type stars still have a long ways to go on the main sequence, since their main sequence lifetimes are longer than the current age of the universe,